the pizza. We haven't met. I'm Reed Essick. In fact, my office is over there, not quite next to the construction noise, but second closest. I'm going to talk today about the nuclear symmetry energy. I've put a list of archive papers in the far corner. Notably, on all these papers, Phil in the back, co-author. So you can ask Phil hard questions if I can't answer them. And as I mentioned a little bit earlier, beyond the science concept of the talk, I want you guys to think about the way I present, what works on a blackboard, what doesn't work on a blackboard, and we can talk about, oh, this didn't seem to work. If you hate the way I present this, tell me that. That means that I'll do it better. But so getting to the science, right? So nuclear symmetry energy. We took a poll of the room. Most people have never heard of this. So we're going to start from a pretty introductory level, sort of work up. And the real question we're going to try and answer is, what is it? Why would such a thing matter? We know what it is. And then how might we constrain it with different observations, in particular astrophysical observations? We are in a theoretical astrophysics. Okay, so what is it? Let's start with that. The picture I want you to have in your head is we're thinking about bulk matter. So surface tension effects are not important. You just have an infinite volume of matter. And this matter is often called NPE, neutron, proton, electron, like 3 species, fermions. So the other things, what do I know about this matter for astrophysically relevant systems? Well, I might expect there to be charge neutrality, which means the number density of protons is equal to the number density of electrons. Okay, important point. Printed N is neutron. Script N is number density. I've thought about a better way to write this. I didn't know. But the charge neutrality basically means that I have equal numbers of protons and neutrons, so there's no macroscopic charge.
And then no antiparticles.
In this. So just for a simple, so in case people didn't hear, because that's other antiparticles like that, I'm only going to consider NPE for the standard matter. At the end of the talk, after that question again, we'll talk about muons and other things. The other thing that we're going to expect that the system will be in beta equilibrium. Which I'm going to define this way. So the chemical potential of neutrons is equal to the chemical potential of protons and electrons. The system will tend towards this through beta decay or inverse beta decay. And so this is going to be my criterion for sort of setting the composition. And then the last thing is, now I have an expression or an equation for this. So I'm going to assume very cold matter. And cold here, I mean that the temperature, the thermal energy that is available is much smaller than the Fermi. Okay, so there's basically you're going to do Pauli exclusion level filling, right? Because these are all fermions, they can't have one particle each thing. You're going to fill up your levels, so you run out of particles, and that's it. There's no sort of thermal jitter around. Okay, so these are the 3 things that. Okay. These are the 3 things that basic structures we're going to have in our head. And if we think about having a box, then we can put either neutrons, protons, or electrons in, right? Some finite density. What this means is that as I add things, I have to add protons and electrons in pairs. And I have to add things such that the number of neutrons in the box compared to protons and electrons matches this. So this is the picture we have in our head. We have fixed volume. I'm going to add particles in it that will increase my overall number density. And I'm going to play the game with particles. So if I think about the properties of this matter, there's going to be some sort of nuclear interaction, and I want to describe some of the thermodynamics of that interaction. I'm going to write that in terms of the energy, so the nuclear interaction energy per particle, which is too long of a subscript today. And I'm going to say this is the function of the total baryon number density. So this is defined as the number density of neutrons plus the number density of protons, and the proton fraction is this. the fraction of baryons that are protons. And because I'm saying charge neutrality, that basically means that I know these number densities have to be equal. I have two different knobs I can wiggle. How many chemicals are in the total, and then so if I have this thermodynamic potential, it's free energy, I can do things like the pressure, abilities, things like that from this. Different nuclear interactions, different theories will give me different functions here for the interaction energy for part. Few more, so we're gonna talk about this. This is gonna be central. So it's gonna try and relate to that. But a couple of limits that are often we need to define. What is called symmetric nuclear matter, or ESNM over M. This is a function of only the baryon density. It is equal to E over N at baryon density and proton fraction of 1/2. That's this case, you get that I've drawn this. For the equal number of neutrons and protons, there's a symmetry between the number of neutrons and protons. This is just the density. And so in nuclei that make up U, E, and everything, typically we have roughly comparable numbers of neutrons and protons in the nuclei. So this is something that you can maybe probe with crystal experiments, stuff that we have access to. But in some extent, this is just a definition. The other limit, pure neutron matter. Can anyone guess what this limit is? Shout it out. It's actually zero. That's in here. So this is the squares that circle. So if I took all these things and shoved them into inverse matrix, this is another one. Okay. So this would be closer to what goes on inside neutron. And so the basic idea in neutron, so if the density gets super high, right, then these electrons, they actually get, they can't just fit them into the box because they've got so they actually end up in high momentum states. Like if you add new particles in, if you wanted to create, put a proton, you have to put a electron. That electron has to go into a very high state quality solution, which carries with it a very large energy. So the chemical potential of the electron, and if that is significantly bigger than the difference in the rest mass between neutrons and protons, it becomes energetically favorable to say, I'm not going to add any more protons and neutrons, I will just add a bunch of neutrons. This is how you get neutrons. So basically, these things would have the electrons would have to be pressed so densely in such high momentum states, it's just cheaper to make. So you will always have some protons and electrons in basic equilibrium. So this is not neutron star matter. It's pure neutron matter. It's not neutron star matter, but it's close. In neutron stars, there are just many more neutrons than protons. In fact, the proton fraction in neutron star matter is about 5%.
Based on the equations you've written, it looks as though the X is a function of N.
Yeah.
Because you have data. So when you talk about symmetric neutron nuclear matter, you're saying you're giving up on data equilibrium, or
So these are, there's some functional here that would be true regardless of what density or proton fraction. Like this is just defined on theory. It takes two limits and I'm defining. But we'll come back to in real matter, we're not going to be in either of these limits, and we need to solve simultaneously for proton fraction as a function. Okay, so back to my title. Nuclear symmetry energy. This is defined as voila. So it is the difference in the energy per particle for pure neutron matter. What this says is that in the nuclear interaction part, there is some energy cost in going from circle state to square state. I take all of my protons, turn them into neutrons. This is the energy cost that I have to pay in nuclear interaction. So this is a definition that a lot of people use. It's not the only one out there in the literature that is great. What the symmetry. Okay, any questions about this? Okay. So, a little bit more. If we plot number density here, and we have some energy per particle, from 0 point. The 0 here, I mean, the density is super, super small, so basically these things are not interacting, the interaction energy. Relative to that, and this is not going to be a super precise plot, but relative to that, if you plot symmetric nuclear matter, it will look something like this. If you plot pure neutron matter, it'll look something like this. So important things to note. Symmetric nuclear matter has a local minimum. And right here, this is what we call the saturation energy. This number happens to be around 0.16 per Fermi cube. And if you care about physical units, this turns out to be about 2.7 or 2.8 times 10 to the 14 grams per cube, which is water is 1 gram. So the symmetric nuclear energy, the thing that people remember, this is when there are roughly equal numbers of protons and neutrons, so that's roughly the nuclei that we count. People can just test this. There is a local minimum, empirically determined, that is about at this point. And this sets the density scale for nuclei. So any nuclei you pick, it's going to have roughly this density scale. That's because it's almost in the state, and it's going to import the density that we're. Yes.
Say it was empirically determined.
I mean, so you can, like, if you smash 2 atoms together, you make the density, right? And then you can measure properties of the scattering using basically a model for this. And then one of the parameters that you can fit forward is the saturation. You can also just look at like, what is the typical scale doing, right? So if you just scatter and say like how big is this nucleus, how many neutrons or protons are in that nucleus,
To deal with the surface terms.
so real nuclei, you have to deal with surface terms, and they're much more complicated interactions than what I'm here in my very idealized world. But people have thought about that and take those into account.
So to give us a feel how close it's the simple theory to actual measurements. Give me factor 2.
You mean like this
One in the energies.
so this picture, they're meticulously drawn as I did, right? This is about minus 15 in MEV. And that knows that plus or minus like 2%. This number here is about 32. At saturation is this number, about 30. Those are known pretty well. The slopes and all that stuff, besides the fact that the slopes here are 0, not really well known. And so the functional form of this, not super well written down, except for maybe right at what we're going to talk about next. Okay, so this thing, there's a common approximation that is used for the functional form of this. So you have symmetric nuclear matter, which is the density alone. Expansion, that's sometimes right differently. So I put all my composition descendants into this figure out here. But I have 2 functions. And in reality, what is going to be on this thing? So let's take simple limits. So first limit, say x is 1/2. 2 times 1/2 is 1, 1 minus 1 is 0. Way, and I just get symmetric nuclear matter, or this, well, that's the density. So I didn't break it yet. Let's take the other limit, x is 0. 0 is 1. So I have symmetric nuclear matter plus symmetry energy. Symmetry energy is pure neutron matter minus So I end up with. So at least in two simple limits, this is not a horrible idea. And so people have tested this basic structure for the way the dependence works, and it seems to be okay. Like, you worry about including more terms, you do worry about including more terms. But especially if you're right around the neighborhood of saturation, people will have estimates that seems to not be crazy. So the other thing is this. You want to know something about the density dependence. Well, the important thing I told you is that there's a local minimum. So people will write this as something like E naught plus 1/2 K naught. I don't know why they define this way. So they normalize it by 3 times saturation, but it's a Taylor expansion around nuclear sections. And you're going to have higher order. But the thought is that around nuclear saturation, you have a local minimum. So okay, let's expand on there, and then maybe this turns into too big. So we don't have to worry, as long as we stay right in the neighborhood. And maybe I said this is empirically determined. This is really known to NSAT is known to be 0.16 plus or minus 0.007 per kernel. And so if you turn that into, it's about 4%. So if you look at how big this term typically is, given rough empirical measures, this is about at most a few percent correctly. So the next term that you have is already only a few percent, so maybe in especially local in the neighborhood of saturation, I think it's not. Okay. So I have, this is my general theory. Around nuclear saturation, I'm going to write it in terms of this. I now have a basic model for the density dependence of this term. Now I basically need a model for the density dependence of this term, symmetry, the nuclear symmetry. And then, at least in this neighborhood, I will have a model, basically a series of Taylor expansions that is, hopefully good in this. And so what people write is, so again, I do a Taylor expansion around nuclear saturation. When people say the symmetry energy, what they almost certainly mean is this term. The symmetry energy at nuclear saturation, and that number is around 38. I have this L parameter called the slope parameter. Very clever name, because obviously it's related to the density dependence, slope of the density. It's the first order term. Okay. So they have things like number and higher. So from this picture, the symmetry energy just happens to be a convenient parameterization of some low order representation, like few parameter representation of this theory. So you can predict theoretically, I write down some Lagrangian, that gives me some interaction, and you can compute what this energy particle, this interaction energy particle would be on theory, express it in the neighborhood of the equation. This, that would give you a number, and then the experimentalists can go off and do the scattering and worry about the surface effect. Also come up with a number that you can compare them out. So we
I have a question. So I can understand why you had this slope term, because you're expanding around the local minimum.
right. So this is for the symmetry energy, which is the difference. And so the slope here.
All right, I see. It's a difference. Okay.
It's different. So this I'm expanding the difference between. So the symmetric nuclear matter has no slope, but pure neutral matter does. And this is going to come back why I'm just about to say this. So this is just a very important observation. It's one of the reasons why we care about this. Besides just like it's a term in our expression that we want to measure these other things. Any other questions about what this is?
These curves, you said some theorists will write down some Lagrangians, you said QCD interaction with Lagrangian.
That's one way to do it. So the work that's like is listed up there that Bill the co-author on uses ab initio nuclear theoretic calculations that are done in a chiral effective field theory framework, which is a fancy way of saying protons, neutrons, ions, and effective field theory described. Cool. Any other questions? You can find it.
Example, I mean, some people may know. Just a quick organizing estimate, the number density.
Yeah. So inside a neutron star, the typical scale of the core is going to be 3 to 5 times nuclear saturation, and then you run down to 0. So it depends a little bit on exactly what your equation state is. Almost certainly you're not going to get about 10 times nuclear saturation, but you are going to get about 3 for any answer. So this is, in some extent, this is really relevant in the outer layers of the neutron star, or like this particular expansion is respective of the outer layers of the neutron star, not in the core.
Because you have
Yes, exactly. Like this scale expansion. I think of it. Yes.
So at some point you expect this in the energy of the symmetry, if you rather than see the theory come back.
It gets closer. I don't know whether they cross. I don't think they would ever cross. And the reason I don't think they would ever cross is here, I'm always adding neutrons to super high energy states. And here, I can add some protons to lower energy states. So even if there's some interaction, there is some attraction and the protons do. They don't have to fill the high. Yeah.
this like gravity should be just like 2 D. So these are just 2 special cases.
Yeah.
So what is the shape like, along the axis?
Well, right. So if you move along the x-axis, you're basically interpolating.
It was
to-
kind of like a linear.
This is my one. So I don't know how to draw that, but yeah, exactly. So if x is really small, right, then the deviation from this is smaller than the x. Okay, so maybe we can talk about now why we would care about something. Okay, so very heuristically, what I've described is the nuclear symmetry is the cost of turning protons into and I silly mistake, I just erased on the equation of the equilibrium. So if data equilibrium exists, I want to add a particle, right? If it is very expensive to turn a proton into a neutron, right? What that means is that I can still have more electrons in very high energy states before I actually need to make more neutron. So if S is big, this means that I'm going to leave more things as protons, well, a higher group. Conversely, if S is small, it's super cheap to make neutrons, to turn protons. So I'll just make neutrons, because I don't have to have these really expensive. So I'll show you exactly, some equations we
You have to think of this as adding it to the mass difference, right? That's sort of, that's what you need to have anyway to turn the protons into a neutron.
That's right.
In addition, you have the symmetry.
That's right. Right, so it's basically saying that there's some extra interaction in addition to the rest mass difference that you have to overcome, but you can because these electrons are. And there will also be, there will be some terms from here. But so heuristically, you can just see that like the magnitude of the symmetry tells you what the composition is. Right, so if I care about how many protons are present, this is the number that I care. We're like,
This isn't too useful for continuous.
So that's exactly what I'm talking about, a PE matter. So with a nucleus, you have to worry about surface terms. There are all the other bulk for MPE matter. Well, I think it's 80 milligrams. And basically this is the number. If I knew this number, then at saturation in beta equilibrium, I can tell you why. Okay. So that's maybe why I care about this first term here. Right, that's it. But do I care about anything else? Okay, already let me into this. Yes, you do. So what's the other thing that I care about besides what is the composition matter? Particularly for cellular structure, pressure is kind of important. I need to know how much it's going to resist the pull of gravity. And from first year thermodynamics, this should look familiar. So this is just from the first law of thermodynamics. Pressure is the derivative energy volume. If you change coordinate or variables, you can also write this as I don't want to say so basically, at fixed number density, there's a relationship, or fixed number of particles is a relationship with volume and the number density. You can do that. And what you see then is this pressure is going to be related to the derivative of this energy, which is back to the baryon number density. So if we take this and we interrogate this, well, at nuclear saturation, we can talk about this thing as well. So that's first this definitely dependent on M. So the first order derivative we pick up will be this L term. So what that means is that this pressure is going to be proportional to L at saturation. So if you can measure the slope parameter, which is the the first order expansion is the term around saturation, it will immediately tell you what the pressure of matter is in your system. And it turns out that this is going to be true regardless of what the beta equilibrium state is, regardless of what the actual proton pressure is, all of your pressure is coming from just interior dark matter. So hopefully that tells you why we might care about this. It'll tell us what our matter is actually made of, what the composition is, what its pressure is, which I would argue is important for things like cellular. Okay. So the last thing I put up here is how do we measure this? Okay. So the classic way to go about measuring this would be I write down some nuclear theory. So I have some model for D over S. And this is going to be a function of like X naught, L, D naught, J naught, all these other letters. From this, I'm going to get a model of like the pressure, density, and all those things. I will solve the TOV equation, the pressure equation, and I'll get things like mass as a function, radius, mass, stability of the function, all these things, properties of stars, and then I compare that to data. Actual waves. And this forward modeling is like standard literature, many. And so there's a whole cottage industry where basically you change this model. So you think really hard about what physics is doing, you change this model, and you resolve the 2D equation, vary the data, and then you submit the PRL, and it's published. So that happens all the time.
You mentioned that the model isn't good at the coordinates. Yes, it's good for a wide enough range of densities if that project is viable.
It is not. This is my argument. It's not. And so, exactly, Chris said, if we're just using this little expansion, then you can say, well, we'll just take that expansion, like maybe we even add a few, and just let that run up to super high density. what does that do? But you actually are still just making a pretty strong assumption of the form, how many turns you have no idea.
The other issue, I'm not sure you touched on is that even or press boundary, the equilibrium of proton and electron factors much less than that.
Yeah.
It's far apart. Suspension, especially.
In nuclear, yes. People, I have heard arguments that like the fact that around saturation, the fact that this is the dominant form for the proton energy or the proton factor to enter seems to work well, but yeah, there is uncertainty in that. Like, is this exactly the correct thing? Is this has the correct behavior? Like, that's been said. Especially, no.
Just another the other complicating factor, I think, is composition. May not be in matter. But that's why in practice, you're going to do this augment this swing thing with some multiple model that so working directly on the run chain that may not just be like an exchange for the interaction, but
And so if you read these papers, they'll say like, oh, we include rho mesons and like these hyperons and all these things, like right down to the Grandian as the one Greek letters that you forgot existed. And then from that, they basically work through to get effectively some model like this that they're computing. They're approximately do. They often verify this in terms of pressure versus mass density, mass density, or number density. Yeah. Then they solve the cases. But basically, people build a lot of complicated models. Choose what the properties of the star would be. Got it. And so, if you're willing to make assumptions about what types of theories are reasonable, effective interactions, like trafficking at the high densities, like that is a program that can be very well. But if you take a step back, exactly like you said, like, well, maybe you're just guessing and checking on the best way for every problem. If you think about this, if you had perfect data, perfect observation, this is going to give us a mass radius curve. We're going to learn something about the math stuff in front of us. As it turns out, there is a pretty strong argument that if you know something like mass radius perfectly, there's a one-to-one mapping between the energy density pressure, the equation state, and that mass radius. So if you had perfect data, at the end of the day, what you would get is something like the energy density, which I call would be the energy divided by the versus the front inside the coordinate. So this is also with AD. So this is what you're going to observe, like this, perhaps if you're after this. So is there a way to take this, a direct observation of this, and then convert it back into this language that I spent half an hour talking to you? So yes. So the way we do this is, I'm not going to work through all the core details, but I'll set up the basics. So the interaction energy is E over N at some number density and composition in beta equilibrium is the energy density of the whole matter in beta equilibrium minus the energy density of electrons. We only worry about the nuclear interaction. And this is at the number density of electrons, proton fraction minus under neutrality. And we get the units right, so I think energy per volume divided by number per volume. And then the last thing is this is the total energy. It's the 20, this is cracked. So what this means is if someone measures this, I pick a density, like so at that density. If I knew the composition in the equilibrium, then I have a measurement of this. This is like the mass of the neutron, it's about a CV, whatever you do about. So if I knew this, then I could just do it. But I don't know the composition. Okay, so I need something else. What else can I use? Well, beta equilibrium. And so what do we need for beta equilibrium? We need P and Okay, so I just wrote this down without really explaining how I'm computing it, but basically you can model this as degenerate Fermi gas. So the same thing here. This would be like a Fermi gas. So the chemical potential, energy density, pressure, all the elements, they depend on the number. But I still have to compute these. So what I do? Well, I know that this is EE, the NT, point, again, from the command. And so I can then rewrite this as breaking apart total derivative. But now this is something that I can grapple because at least in the neighborhood of saturation, I believe I have an expansion in terms. So I can define a similar thing here. And volume. So when I plug that in with my low expansion here, theta equilibrium ends up giving me derivative of the interacting energy per particle back to that minus equal to rest mass of the neutron minus the rest mass of the proton minus. Which basically, I mean, this makes sense. This is saying like, as you change your composition, what are the things that matter? Well, the difference in the rest mass is like 4%, and then the chemical percent. Okay, so when I take this derivative, like this equation is actually completely general. If you just follow through with the calculus, but then I need to plug in a model here. So I'm going to use my model over here. The only derivative constant. So I end up with minus 4, 1 minus 2x as equal to. So this thing, I also have a model for. This is E matter over n 1 minus 2x. Okay, let's take a step back. Everything in blue, I measure on here. Everything in yellow, I model the Fermi gas. Everything in orange, I measure astrophysically. So because I have access to the symmetric things that matter, light, materials on Earth, and like I said, out of the way of physics, they have an idea of what the K naught is. I have here and E. So if I look at this, I can pick a density. As long as it's nearby saturation, all of my expansion is not sorry. But pick a density, I then have astrophysics input, so I'm modeling a bunch of things that I can measure on the Earth. 2 remaining unknowns. What are they? They are X and X. So from the system equations, like 2 equations, point known, that self-consistent to solve for what the symmetry energy is at n and the associated proton fraction at that. So if I do this for a series of densities that are all in the neighborhood of nuclear saturation, I move it in the decimal neighborhood, then I can trace out in that little neighborhood density dependence of this curve. That I can do derivatives, so I can go from S to L A. And so programmatically, instead of having to come up with a nuclear reaction, and then forward pop. I can pretend that my data is telling me exactly what this curve is, or I have some distribution over curves that the data supports. For each one of those curves, I can set up this equation and near equal saturation, where basically this bit is where I've used my expansion here. So where that expansion is supposed to hold, I can then solve for this, and I can extract these from an arbitrary equation. So the last thing I want to say is, what does this look like? What do the actual constraints look like? Again, carefully crafting this plot. My plot L here, typical numbers are 30 to like 70 MeV, as you'll see theoretically people predict. My plot S naught down here, the typical number is around 32. But it's plus or minus 1. Terrestrial experiments, a whole combination of them, you can like slap them all together, overlay them, you'll get an uncertainty that roughly looks like this. And so it's centered around like maybe 30, 40, depending on exactly which data you use. So this is something like experiment on the Earth. The theoretical models that Phil and I worked with in the papers, if you overlay them, they will give you something like this, spiral EMC. So it's not a perfect overlap with experimental data, but there is some overlap. Can anyone guess what astrophysics will give you? Bottom. So it's yellow. Astrophysics gives you. And so what's going on there? Well, the basic physics is exactly what we've been talking about. This expansion, all the stuff that we carefully crafted this model, holds around nuclear saturation. As Norm said, the core density is like 3 to 5 on nuclear saturation. There's a lot of physics there now. And so the papers up there, we very intentionally try to build in one of the minimal assumptions, physical assumptions about how you're connecting these densities. So what we assume is that the EOS has to be stable. So sound speed has to be positive, pressure has to increase. And it has to be positive, which means the sound speed can be faster than speed. That's it. And in reality, we have a couple other assumptions that are built in, but those are the only things that we try to build in. Super loose, like assumptions about what actual nuclear theory is doing. And when you do that, you get a posterior process over the possible equation states, subject to two very loose theoretical things. Work your way backwards, do this extraction, make a plot. It looks silly, right? But that's intentionally what sort of we're trying to do. We're trying to say that the astrophysics, very basic physical mechanism, you can't really explain. There are people out there who, like as Phil said, will make assumptions about a particular effective interaction. And then what they find is there actually is a tight correlation between things like L and the radius of neutron stars. And so if you measure the radius of the neutron star, well, you would learn something about that. What we find out is that that correlation is actually so broad that for any L you pick within reason, you can support any neutron star radius at like relevant astrophysics. So there's actually not that. Like you are, the reason that you're seeing correlation is because you made some theoretical assumption. Now that it's a very good idea if you want to test a theory and see if does it explain all your data. But if you're taking an agnostic approach, then you have to be careful about exactly what you're claiming because you are actually doing terrestrial experiments plus astrophysics plus some connections. So Chris had a question.
Just this yellow
Yeah.
circle, is that current astrophysical data or perfect future astrophysical data? Does it
This is-
include information from, tidal deformability?
So tidal deformability, gravitational waves, mass radius measurement from X-ray timing for one of the pulsars that night public. And this is Shapiro time delay measurement, so radio. Yeah,
Maximum masses.
Yeah, 7 volts. So this is the set of data that we use to get this current. There is a little bit of extra, like nicer has enough target, nicer stare at this guy, try to get a radius for that. But this is also the most massive neutron star we've seen. So it's at the highest density. You expect that like the fact that the radius might be up there won't change this stuff at low density. But yeah, this is current data. We do have a plot in one of those papers where what if we have like a perfect measurement of L? Not exactly what you said. But what if like someone built the best particle experiment really got L? Excuse me, how would that affect our knowledge of neutron star properties? And really it shifts the mean by a little bit, but that little bit is like a tenth of a sigma. So the uncertainty that remains from that is so very broad compared to what such a tight has done. Other questions? Basically.
So
Yes.
that measurement is based on one neutron star.
No, so this is 2 neutron stars that collided. This is 1 neutron star, and this is 1. So 4.
So why is it that the sample is so small? Do we not have more observations of neutron stars?
So yeah, so we can use if you're talking about you want to know what the maximum mass is, basically you're always dominated by the biggest figure to see. Right? So you're gonna have like one, maybe a handful of neutron stars here that really limits the maximum mass. At the time of publication, NICER had just barely released their second observation. But if you guys aren't familiar, NICER is an X-ray timing experiment. It's about the size of a washing machine. It's strapped to the ISS and it stares at neutron stars. It counts the energy and time of arrival of their X-ray emitted from the surface of the neutron star. It takes time to beat down on the noise and just integrate that up. And you have to worry about things like the sun coming into view, so you can't observe all the time. So their first publication is in 2018, 2019. This is still pretty new. It's taking time. And we haven't been lucky with gravitational waves to see more than really this is the good one. There are a couple other ones that might have neutron stars in them, but this is the only one that we've really seen a pretty clear signature besides. Even for this one, that signature is not unambiguous.
Point nicer.
Yes, you can point nicer at whatever you want.
And the thing they do this whole modeling of the like gravitationally bent light curve, you have to believe quite a lot to believe.
No, I understand that, but I mean, if you want to constrain this as one have any event saturated, so that means I think you want the sort of lightest neutron starting point.
So, right.
Are they trying to target light neutrons?
They're trying to target heavy neutron stars. And let me tell you why. The tidal deformability from gravitational waves scales very strongly with the mass. So this thing, the tidal deformability, is what we measured. After Phil about this, they had a computer that did that. So the tidal deformability gets directly imprinted into the gravitational waveform. So this is what we observe. We call this thing capital lambda. And typically this scales as mass to maybe it's not. What this means is that this number gets really big really quickly. Your measurement uncertainty takes roughly. So you get a relatively precise measurement from gravitational waves. So the thought / hope / desperate prayer is when we turn the gravitational wave detectors back on this year, which should be like May, we'll just see a bunch more binary neutron stars. It depends on what nature makes, but we're hopeful to have a couple light ones there, and then bam, we'll get the low mass behavior link. The NICER knows this, and then like we're not going to compete with that. But the converse of this is at high masses, this is a really small number. You get a very imprecise. The error on the radius doesn't. The radius doesn't behave as good. Radius is roughly constant. The error will be roughly constant. So it makes more sense for them to integrate down on high mass stuff, and that's how they're going to make progress. And then they'll just pick up whatever gravitation they publish and give the best. That's sort of their game plan as far as.
This assumes you're lucky. Light neutron stars merge.
Yes,
While you're
and
looking
that
at-
cross-checking is not necessary. It seems really, really weird.
Well, the first pulse of the division was the same.
Right, that's nice. And I'm pretty sure they're doing all 437 too, and also very well.
The light would be great, yeah, exactly. But if you know what masses are stars. Seems like a weird strategy.
Well, so I think what they did is they did this one because it was the brightest,
Yeah, sure.
and then they did this one because it was the biggest. And then while they were publishing, so there is a nicer observation of this. That's happening. And then while they were publishing that, they just, they have like a half dozen targets, and they've just taken data on a bunch of these, but then there's some political process for which one they work on first.
I think generally speaking, they're going to try and pick on stars that we are not seeing the gravitational waves, so that they can be maximally complementary. Right? And based on our hunch, that's going to be the high mass one. But if we, I don't know, aren't seeing the low mass ones, then they have a nice hand.
Yeah, I think that their plan would be, their game is you want to measure the mass radius for all and many different masses. Then you get the full shape, and they will probably want to do that independent of gravitational waves. It's just which order are they?
So you don't believe ray tracing? GR?
I don't know that I believe that they understand the atmosphere well enough to know that your emission is isotropic, or it's probably not isotropic, but to what extent it's not isotropic, given that there's a magnetic field on there. Otherwise, there wouldn't be pulsations. There's freedom. Yes, and the magnetic field geometry is not known.
Go right.
It's also been
The built second pulsars, so there's
Exactly. Yeah, I think it's great that they're doing it. Don't get me wrong. And anyway, they're also the globular cluster neutron stars where one has a pure hydrogen atmosphere. I think those are not bad. They're sort of consistent with the radio. I'm not surprised that you got that curve out. It's really hard to do it
Are
well.
they using millisecond pulsars?
The globular cluster is sort of cooling neutron stars, which start out, which are transients and are now cooling down. So hopefully nothing is happening.
Yes. So the nicer targets, I don't know if they've gone after, they probably will go after like, as long as they can get a good X-ray, like the fastest thing that is known to be an X-ray pulsar.
Yeah.
That's obvious that they're gonna do that.
Right.
But I think that the spin period of this is like closer to 10 milliseconds rather than 1 millisecond. It's fast, but it's not super fast.
And a millisecond pulsar is always a bit of a mistake. None of them are actually milliseconds.
oh,
Well, I don't know. 1.6 isn't that good enough.
No, it isn't.
Yeah, so if you want to talk about the details,
Well, that's, yeah.
and so we have evidential QT calculations that people would argue go up to maybe 2 times that. Really, it's chiral effective field theory, which is derived from. But so with error bars equipped, you can maybe do a theoretical calculation point sensor. That's not high enough.
the limiting factor there is your ability to do QCD.
Did they do lattice gauge numbers?
So the lattice QCD calculations are typically good and well controlled at low baryon chemical potential and high temperature, which is like the opposite side of the phase diagram for neutron stars, which are high chemical potential, and so high number density and low number. So it's hard to do like a lattice calculation. The chiral effective field theory, they just write down I have neutrons, protons, pions, all the interactions that follow my theory, fit those to some scattering and mass data from the Earth, and then basically have some uncertainty in what those coefficients are in your effective field theory, propagate them forward with their estimates. That's their game.
And have people check that against the in the opposite limit where you do that as QCD and get these results.
Probably, I can't give you, so I know of one reference where people have looked at complete arbitrary proton fraction, arbitrary temperature, chiral EMT calculation, but then
It's always good to check the theory against thinking.
yeah. And so like there's like a whole separate program about chiral EMT and how well they know this and like what's breaking down the theory, where, but the reason why people say it can't go above 2 times saturation is basically because there's a breakdown scale of this effective field theory where you have some, if people are familiar with it, basically you're saying you have some expansion for the interaction. You have some operator, effective operator that's like sum over some momentum divided by some breakdown. And you're gonna call it, you're gonna do your calculation by truncating this sum. Right, and as long as your momenta are much smaller because of the breakdown scale, then the terms that you think like this are probably bigger. Well, the breakdown scale of this thing happens in nuclear. Corresponds to roughly densities. You get like the atom content. So if you truncate the calculation at all, your areas blow up. So the theory basically was not predicted because of like, we don't exactly know why, but there does appear to be a preferred breakdown. That's over like 680. So that's what's limiting the low density stuff. People do conservative QCD, like honest to God, pure QCD, but where they think they can control that is at like 40 times. A little too hot for this. Like neutron stars are going to get up to 5, 6, 80. So then there's an effort for people to take those calculations back the other way, but then there's arguments about how we're doing that stitching, how you use it. There's a lot of physics that could be going. Okay, I want to leave at least a few minutes for the last of the discussion. What do people like about this? The talk style. What people think worked well? Would this work well in a lecture setting, undergrads? Or did I pitch it more towards competent experts, like postdoctoral level? Shout out. Intro grad.
Or very, yeah, like a mezzanine. Here. I just thought my undergrad is about neutron stars, and I did not get further than the Fermi energies because we had discussed that. I think this is definitely beyond the third year undergraduate level here. The fourth year maybe they're really interested.
Our graduate students.
Tom.
Yeah, Tom, how's the music? Style, one thing that I really liked was almost everything stayed on the board. So I could look back to what was newly introduced, but I forgot what it was 5 minutes later, and then keep on following. That was very helpful for me.
Contrary to that, I have trouble with far side of the board. I still can barely read it, but so I think you got a little bit on the small side there. You need a room with these 2 blackboards.
Yeah,
I love those. That's just
I mean, I should probably write larger.
I might have done the why before the what. Because I had the strong sort of anticipation that I would learn something important was about to happen, but what it was going to be was a mystery until halfway through the sem.
Like God, you don't see the chart. No, that's a good comment. Yeah.
I guess that's one thing that to me that I actually don't know, so I might as well phrase it as a question. And obviously, this stuff also comes in atoms, right? There's a reason there. Half neutrons, half protons. And I think I would have made maybe that connection a little bit more. The sort of say, well, why don't all nuclei just consist of protons? That's it's not quite the same question, but it's very similar. So maybe sort of make a connection to. You did quite a lot of it, which I liked. Of sort of things that one does know.
And you've drawn that curve for the symmetric nuclear matter. We could to sort of get one intuition. First of all, why it's negative compared to positive, and then such as a gravity. Then why is there a reason for that minimum to be at that energy?
It's not gravity. It's a strong nuclear attraction.
It's good.
The upper.
Yeah, I don't think that. I think it's positive. Basically, what that's telling you is that a system of neutrons would just not be bound.
Yeah, but why is it neutral? And that is, so what I'm really hearing is that I should be more background. Yeah.
Should explain the nucleus quickly.
Yeah.
And the trends once observed within nuclei of different masses, and then go to continuous mass.
Right.
And it would be good to explain the equilibrium electron fraction in neutron star.
Well, you sort of did.
Not good.
This is the thing. Like,
I mean, basically you can get it with this approximation to start taking non-interacting from the gases.
Right, but on the other hand, you did spend, you did spend about 50 minutes, so if we ask you to add a lot.
Yeah,
we have, but yeah, I think that's a similar comment.
Right, but this is a good point, like, you know, how many times do people think that I practice? You think less than 10, more than 10?
Oh, that's.
It was a nice spot. It was a nice spot.
No. Right, but so I practiced about 4 or 5 times, right? So I kind of knew the path that I was taking. But even though I practiced it and I thought I was explaining things clearly, different people in the room got different things out of it, right? And that's always gonna happen.
Yeah.
So having, like, what we said, the things that I called back to, I didn't do that perfectly. Like, I erased things I shouldn't have erased. Okay. But thinking about how you're gonna structure a talk, particularly if you're trying to convince undergrads that this is interesting, maybe like Chris said, maybe I should do it on the why, or what first, things like that. Just, you know, keep that in mind if you're ever giving a lecture to. So I don't want to I've kept people a long time. If you want to talk about the styles of the talk or more questions about the science, I'll around and stick around. But thank you guys for listening.
The probably the professor said in my class